It is very, very close to 2 hours UTC. It is 2 hours UTC. It's 2 hours UTC, which means it must be time once again for Astronomy Daily Live. This is a live stream, happens every single day at the same time, which is right now, 2 hours UTC. Hey, everybody, glad you're joining the circle again, this circle of astronomy passion that uh, never ever goes away at all, because astronomy is, hey, the study of everything. So very broad, but very, very fun, casual, fun, educational, skeptical, open minded. So that is the definition of science as far as I'm concerned. All of those things. And yeah, bottom line is have a lot of fun, enjoy, you know, quit fighting about so many things. It's ridiculous. It's okay to have differences of opinion, and if you don't want to interact with particular people or groups, fine. Just leave each other alone. Easy enough. Easy enough. There's more than enough to go around, and once more of us realize that, we'll be much better off, and we'll be able to get on with things, have a good time, have fun, enjoy ourselves, extend our lives. Who knows? Travel to the stars. Yeah, why not? Hey there, Uncle Bill. Hope all is well. Uncle Bill is a great supporter of the show. Um, Uncle Bill, I know that there are more like you out there. So, yeah, I think it's just a matter of patience, perseverance, and uh, my um, core group will be found. Will be found for sure. So, yeah, come on in, join the circle of friends every single day, the same time, 2 hours UTC. Glad everybody can be joining live. I'm glad for those future viewers. I know that this isn't a great time for everyone, but the choice of a time has to be um, sort of arbitrarily chosen. This time is convenient for me, so since I'm the host, uh, it's sort of the easiest for me. Times can change. Maybe I'll go to twice a day. Who knows? Who knows how this is going to go in the future? At the moment, it's follow my nose and just try to get better every single day. So that is the goal at the moment, is just to get better and better at this. So cheers. Tonight is another hydrogen hydroxide night, HOH. So cheers. What a wonderful and awesome chemical this is. There's some deuterium in here too. Statistically speaking, there is going to be both um, deuterium and hydrogen in this. So there's a little combination of heavy hydrogen hydroxide and regular hydrogen hydroxide. I guess that would be called DOD, which is deuterium. I don't know. I don't know how to pronounce DOD. So I'm gonna have to find that out. Another means of learning something new, and that's another thing that this show is about, is curiosity. Um, in fact, I like to call myself a curious participant. Um, there there's another show um, sometimes I watch that has sort of uh, the odd name suspicious observer, and I just think that's that seems to be a little paranoid. Um, it's like you're watching things, looking around, the corner, and it's like, what is that? Got to be afraid of that. And I'm not about that. I'm about being a curious participant. I want to dive right in because it's like, what the heck is going on here? And whether we like it or not, we are all participating. Uh, you know, you might call yourself just an observer. There aren't any observers. We are all um, participating in this universe. We are like one side of a coin. It's like on the one side is me, and on the other side is the rest of the universe, but we're all part of the same coin. So, if you want to call yourself an observer, yeah, that's okay, but I don't think you are. I don't think you are, because just by observing, in fact, quantum mechanics says that if you observe, then you are participating. So, uh, yeah, I would much rather be a participant, or at least see myself as a participant, than an observer that's suspicious and all that. I'm curious. I'm curious, and yeah, I'm going to put my hand in the fire, and you know, you get burned. You get burned that way. But if you learn, okay, if you have just a tiniest bit of intelligence at all, you learn from that. And it's like, oh, okay, hmm, won't put my hand in the fire because, you know, I like my hand. So, and I want my hand around. So, uh, yeah, Uncle Bill, um, he's got a big following because well, Ben is really smart. He's a smart dude, and definitely shout out to him for sure. He has a paradigm, and I like I like to have a variety of paradigms and points of view. I think that's also good science. And if you box um, yourself into one um, paradigm, I think you are limiting yourself. So yeah, I think he's great. He he he's got a um, pretty big following. I think a lot of people, share his views in sort of being afraid of things, and looking out for the next disaster. And I yeah, I think that's okay. Serves a purpose, and he's very successful in all of that. And yeah, very cool. But as I said, I'm more of a curious participant than a suspicious observer. So as I said, quantum mechanics says that um, being an observer makes you a participant. So cheers to participation. So I wanted to continue talking a little bit about the project that I'm doing in parameterizing my telescope back here in CCD. And as I as I was hoping to do today, uh, I looked at photometric things. I looked at the brightnesses of the stars, measuring actually the brightnesses of the stars in one of the fields of view that I took a few days ago. It was actually on the 7th, so that was or on the 5th. So that was what, 5 days ago now. It's been had we had a couple more clear nights, and um, and now it's been cloudy. So I don't have any new opportunities to collect more data, but you know, at the moment, really, I've got a lot of data, and I've I've looked at basically just a couple of images out of probably close to 100 now. So I need to look at the rest. The thing is that this kind of work, and this isn't uh, what a lot of astronomers talk about, is sort of the tediousness, the absolute painful, mind-numbing tediousness of analyzing data. It it can be just, as I said, very very mind-numbing. It's a lot like, well, it's got a similar flavor to practicing music. It's a lot of um, repetitive, over and over and over again, sort of the same thing, uh, over and over and over again, and yeah, it's the work, it's the actual work that leads to you know conclusions, and hopefully increased knowledge and all of that. So today's task was to see how good my measurements of brightnesses of some of the stars in this partial field of the open star cluster called M41, Messier 41, a very, very nice binocular object just south of the star Sirius. So take a look at that. I think probably even in the cities, you can see this cluster as long as you're looking in a pair of binoculars. So if you're at a really, really dark site, you can actually see its naked eye. But yeah, get a pair of binoculars or a telescope on it. Easy to find. It's just south of Sirius, maybe 2 or 3 fingers down or so. Um, so yeah, beautiful cluster. Uh, I like it because it's got sort of a variety of bright stars and faint stars. And so what I can do um, um, right off the top is I can measure relative brightnesses. So I can take one star and say, okay, this this has brightness X, whatever it is. And then I can measure the brightnesses of all the other stars relative to that star. And so I can get brightness or magnitude differences there just by um, um, doing a little bit of math and that. So then what I can do, I can make all those measurements, and then I can compare my relative magnitudes to a catalog of stars, which I presume has the correct magnitudes in it. And so I can compute exactly the same way um, the relative magnitudes uh, from this catalog, and then I can compare those magnitudes to my measured ones, and I can change the technique as to how I make the measurements. I can change my code. I can change the algorithm. Lots of things I can do there, and then I can compare those two things. So that's sort of what I'm showing with this first plot that I posted onto my Discord channel, which you can see. Uh, there's a link down in the description. You can probably see that down there. That will get you there. I invite you to join that server. I try to post things there as often as I can. Um, anyway, so what this plot is showing is I'm not gonna be able to make it big. So along the x-axis here is the relative magnitudes um, or magnitude differences uh, of 32 stars that I identified in my field of view, and I found those in the Gaia catalog, and of course, they have magnitude measurements on them, and I look at the relative ones. So I chose one, which is actually this one here that has a relative magnitude of 0, because in relation to itself, of course, there is no difference in magnitude. Um, and so these are all the other stars. And what I did is I measured the brightnesses in my data 3 different ways, choosing 3 different uh, um, um, sizes, 3 different areas um, to measure flux. And so this plot, yeah, so that's what I'm showing here, is that these are the magnitude um, differences that I I measured, is along the y-axis. So these are Gaia's, and these are mine, and and I did this for three different methods, and so I've marked those with black dots and red dots and blue dots, and as you can see, um, uh, some of these sort of just look blue, and the reason why is because all three are stacked on top of one another. So I plotted them in order: black, red, and blue. And so the last one um, uh, um, is going to be on top, and so you're not going to actually see black and red. But what that means is that um, the measurements for this star all pretty much agreed with one another, and uh, uh, that's how it measures up in terms of its relationship to Gaia. So as you can see, these scales aren't exactly the same, right? This is going from 0 to -1. This is going from 0 to -2. So -1 is about here, and so this is around what, like point, like negative maybe zero point 0.7 or so, and so is this actually. That's sort of why this line looks so straight. If you were to draw a line here, that's why it looks so nice and straight. I probably should have scaled these in a different way, and maybe I'll change this plot so I can go from 0 to -10 and 0 to -10 to really show that relationship. But what I'm finding here is that on average, I'm seeing a difference between these two of about maybe 0.3 magnitudes or so. So that's not incredibly great. That's not too bad, but have to realize um, that this is completely uncalibrated data. So this is just raw data right off of the camera. It it hasn't been calibrated um, in any way to subtract the dark and to flatten it out and to subtract any electronic bias or anything else. So the fact that I can you know um, get a precision of about a third of a magnitude, that's not too bad. It's not too bad at all, especially since, as you can see, I'm I'm doing a pretty wide span. This is like almost 8 magnitudes difference here, and I have to say that this faintest guy out here, this faintest guy, which, yeah, isn't really on the line, right? He's pretty far off the line, but this guy is almost yeah, actually is 14th magnitude. So I'm seeing 14th magnitude stars, pretty big error. Yeah, I think the other thing that I want to do is I want to draw this 1-to-1 line, so we can really see how far off this is. But it's pretty consistent, at least, and the measurements, the errors in the measurements get larger as the stars get fainter, so that all makes sense. So I'm pretty encouraged by this. It bothers me a little bit that I'm off by a third of a magnitude, even with the uncalibrated data. Um, but actually, let me look at the data, because I'm talking about a third of a magnitude precision error. If I actually look at the average at the average error, um, yeah, the average error is about a third of a magnitude, plus or minus a third of a magnitude. So yeah, not great yet, but I'm hoping that with some calibrated data, uh, that'll actually look a lot better. This is really hard stuff. So it's if it was easy, everybody would be doing it, and it's not. It's really hard stuff. Cheers. So yeah, I think I'll make some improvements to this plot, just so it makes a little bit more sense. Just talking about it out loud here, I'm like, yeah, okay, I need to make some improvements to this plot in order to better understand it. So yeah, I will definitely get on that in the next couple of days. Let's see, what do I have to do here? I have to exit that out and go over here, and we can look at. So the other thing that I did, and I actually did this yesterday, was I looked at the positions of all these stars, of these 32 stars. Looked at the positions of them and measured their positions as well, and found that the um, the differences between my measured positions and the published catalog positions of these stars were, for the most part, uh, less than a pixel in size. So my astrometry is really good. That's very encouraging. Doing astrometry is a lot easier than photometry, because you basically just have to measure the position of a dot, right? And that's relatively easy. You don't necessarily have to measure how bright the dot is. You don't have to necessarily worry about seeing or any kind of optical effects. Um, don't really, you know, having calibrated data isn't quite as important. I and I have to remind you that all of this data that you're seeing now is with the uncalibrated um, images. So not too bad that I can that when I compare my positions with Gaia, those differences are uh, less than a pixel in size. That means that the astrometry is very, very good. Now there's an outlier up here, but he's also very, very faint, very, very faint. So, but still, 3 arc seconds, not bad, not bad at all. So I'm really, really pleased with this. This red line here is my pixel scale. So uh, with 1 by 1 binning, um, I've got like 0.986 arc seconds per pixel, and of course this value here is arc seconds, and this is just the target number. As I said, I've got I identified 31, sorry, 31 targets in this field of view. I uh, I didn't post I didn't post a picture of the actual field of view. You know what? I can do that right now on my Linux machine. I'm going over to my Linux machine and I'm going to pull up my Discord over here, and I'm going to go to that, and then I'm going to go to, oh, do I have this over here? Ooh, I don't know if I have a picture or not. Let's find out. Let's find out. Oh, I do. Yeah, yeah, yeah. Yeah, I do. So, oh, let me do this one. I've got one that shows all the detections, and then I have just the raw image. I'm just going to post up the raw image here. There we go. Cool. I like being able to do that live like that. That's pretty cool. It should pop up here, I would think. Dun, 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 dun. Momentarily. Is it going to pop up? I did put it there. Let me move away and then move back on it. There it is. So this is the image that I used to measure, the brightnesses and the positions. And I did everything relative to this brightest star. So this star here, at least according to Gaia, let's see, I'll look at that. According to Gaia, the magnitude, the brightness of, oh, that's astrometry. I need, uh, there it is. Yeah, so the brightness of this guy is magnitude 6.29. Next brightest one over here is 6.99. Next brightest one is 7.86. On and on and on. I don't remember which one was the 14th magnitude star, but it's going to be one of these guys. And you know, uh, as I said, I think I understand why my magnitude measurements are a little bit off, although a third of a magnitude is not bad, not bad. But I definitely want to be able to, calibrate down to, ooh, less than a tenth of a magnitude. I would like to get into, maybe the tens or, yeah, tens of hundreds of magnitudes. So yeah, I mean, if I can um, get the measurements down, to like a hundredth of a magnitude, then I can actually uh, uh, look for uh, um, exoplanets, which isn't really something that I'm interested in, but that is the level of precision that I'm after. And yeah, I've got a little ways to go in terms of that. I've got to go. I've got to improve my um, photometric measurements by a factor of 30 in order to do that. So that's going to take a combination of good calibrations. See, as you can see, you know, this is a reversed uh, um, image. So dark things on here are actually bright, and bright things on here are actually dark. So as you might be able to see, it's a little bit darker over here, which means it's actually lighter over here than it is over here. See, so this has a general slope this way. So what that means is that when I measure, say, the brightness of this star, okay, well, it's it's seeing a little bit of this brighter background, so it's going to be artificially brighter uh, than the measurement. Well, than if the star were over here, see, and this is going to be sort of the opposite, right? This is going to be um, slightly darker than what it should be. But once I flatten this field out and you subtract the darks out, um, and look at the algorithm that I'm using um, to measure the fluxes here. Um, we'll see. We'll see. As I said, my goal is 1/100th of a magnitude precision, and yeah, as I said, I've got a ways to go. I've got to improve this by a factor of 30 to 40 in order to do that. But even if I can get um, less than a tenth of a magnitude, when I'm getting into zero point 0.09 magnitudes, zero point 0.05 magnitudes, that's pretty nice too. And if I can have that kind of accuracy and be consistent, then I'm going to be a pretty happy camper. So that's sort of where that project is. Really, what I have to do now is the incredibly mind-numbingly tedious task of looking at more of these images. These are 2-second long exposures taken with no filter at all. And I've got 30 of these. Okay. Well, I spent today, not all day, but at least a couple hours on this one image. Okay, I've got 30 of these. And then I've got several other sets. Let's see, A, B, C, D, E, F, G, H. So I've got 7 other data sets that have 30 images each, taken with different exposure times and different filters, slightly different um, fields of view, sections of M41. Um, Basically, the same stars. I want to be able to compare apples to apples, and so that was important. But I spent a couple hours just on this one image, right? So if you multiply that out by what 210 of them, that's like what 400 420 hours of time. So it's just tedious work. Um, and but one of the neat things about being a programmer is that after I do this a couple times, I start thinking really, really hard about how I can automate the process, and just through a couple of repetitions, I can start seeing where I can be like, oh, okay, I can I can encode that. I can write some code, to do that for me. So usually after I do this a couple times, it's I just don't want to have to go through this manually each time. So I'll come up, with some kind of a script or some kind of a program uh, that I can sort of use, to do this automatically. And so definitely for sure, I will not be spending 420 hours. Um, I'm looking at all this data. Rather, I will spend 420 hours figuring out how how to make the process easier. So that's usually how that works out. Cheers. But this is great fun, and as I said, it's part of a larger project that I'm trying to finalize. There's some additional data that I need in order to sort of finalize this. So I'm essentially just waiting for a clear night now. But we've got some clouds and some rain moving through over the next couple days at least. So I don't know when I'm gonna um, get to it, but as you can see, I've got enough work here to keep me going for quite a while. It doesn't take a lot of data to produce a lot of interesting results and a lot of work, and that actually is a great segue into the interesting paper that I found looking through archive.org. Um, Found this really cool paper on a runaway yellow supergiant star in the Small Magellanic Cloud that I thought I would run through tonight. I've been looking at this afternoon, so I'm at least a little familiar with what they're talking about. Well, sometimes these mice get away from me. I'll zoom in on this a little bit more. So these folks were doing were sort of doing one project and got got distracted a little bit um, when they found this very unusual star. The star I mean, it just stood out, and I'll show you a picture here in a minute, uh, making that incredibly obvious. But they were basically, I'm just doing a survey um, looking for yellow supergiants in the Small Magellanic Cloud. The SMC is a dwarf galaxy. It's a companion galaxy to the Milky Way, and they they were just looking for a population of stars, um, and they found this really weird looking one. And so this is just the basic paper, right? Um, they uh, they talked about, you know, how they discovered this, and in this paper, all the pictures and all the plots and everything are at the end of the paper. So I'm gonna scroll down to the end and show you the first picture here. And I'm going to have to scroll out a little bit or zoom out a little bit here. Zoom out, zoom out, zoom out. So these are just measuring the um, velocities of a bunch of different stars relative to Earth. And what you notice is that you've got this population of stars here that are um, um, gathered around a radial velocity of zero of 0 kilometers per second. And then you have this other population out here, which are moving what around 100 150, 158 um, kilometers per second. You've got a few. Come on, mouse. You've got a few sort of funny ones in between, and then you've got this one out way out here. So these are um, yellow supergiants that they identified to be in our galaxy, and so relative to us, they aren't moving all that much. Now, of course, there's a big spread here. There's a big spread, but in general, there's sort of a population who who are all basically moving like we are. So their relative um, 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 velocity is hovering around zero, right? But then you've got this other population of stars out here that, relative to us, uh, are moving, and these stars correspond to stars in the actual small Magellanic Cloud. So we know, because we can measure um, the velocities of many of the other stars in the small Magellanic Cloud and see that are also moving at about this speed. So that's an easy way, to distinguish between the foreground stars and the stars that you're actually um, wanting to study a little bit more. Now they took spectra. I don't know if they took spectra of all these stars. They definitely did photometry on all these stars, and they actually published their results of that, which is in this table here. Oh, I'm showing you things. I'm spoiling. So these are photometric measurements. I guess they did take spectra of all these too, because I'm seeing measurements of velocities here. I'm going to have to zoom in a little bit so you can see all of this. So these are all the stars they measured. Here are the names. Here are the positions. See, right ascension is designated by alpha. Declination is designated by delta. That's standard notation. And then there's a K magnitude, and then there's a J minus K color. There's a V magnitude and a B minus V color. Now, looks like maybe some of these things they actually got from the literature, because there is a reference, reference 3, reference 4, and probably it's at the bottom of the table. They measured a lot of stars here, right? They measured the velocities of all these stars, um, categorized them, looked in the literature to see what kind of stars they were. They were, they were interested in looking for a specific class of stars that they're calling um, yellow supergiants. Uh, so that's really all that they were looking for was just wanting to identify these. You know, you have to identify your targets before you can look at them more carefully. So that's all they were doing. They were just sort of casually looking around, trying to identify which stars were which. You know, they don't want to be looking at um, yellow supergiants in our galaxy. They wanted to look at yellow supergiants in the small um, um, Magellanic Cloud, right? So that's what they were trying to do. But one of them stood out, and let's see if I can. I'm looking at the radial velocity uh, column here. This one right here, because one of them sort of stood out. Now this one sort of stands out, 203. There's another one that really stood out. Let's see if I can see him here. I may not be able to see him. I might have to search for his name instead. Where is he? Am I seeing him or not? Da-da-da. Lots of stars. There's always a lot of stars. Huh. Why am I not seeing this guy? Crazy how many measurements they made. Gotta say. All right, well, we'll find it a different way. That's a lot of targets. Lots and lots of targets. But that's a great way, to identify them and sort of distinguish between them. Uh, is to look at their motion. So that's what they did. I'm going to go back to this. Let's see. So what they found, and now I'm going to search for it. They found one star, this guy, copy, and then I'm going to paste into here and search for him. There he is. Okay, so let's zoom in on him. So as you will now see, painstakingly doing this, you can see that this radial velocity is 296 kilometers per second. So that stood out like a sore thumb, and you sort of already got that idea when we looked at this first plot, this one. Look at look where that star is, way out there. They they uh, they were pretty confident that um, this is a yellow supergiant in the small Magellanic Cloud. But look at its motion. It's like no other one at all. So that got them really distracted. Um, it's like, what is going on here? Cheers. So what they had to do is they had to determine uh, they had to determine, first it's like, what is going on with the star? Where is it? Is it Is it in our galaxy? Is it in the small Magellanic Cloud? Is it somewhere um, um, in between? Really, really don't know. Don't know. Um, have to point out that all the analysis and all the reduction of of the data, to calibrate the data was done with IRAF. IRAF is the astronomical tool. Um, if if it makes you cry, well, maybe you shouldn't be doing astronomy, because IRAF is the tool for sure. It and Yeah, it's hard to use, but doing astronomy is really hard too. So if you can't handle IRAF, mm, think think about a different profession, maybe. So just my opinion, of course, but yeah, IRAF is an extremely powerful tool. Um, IRAF stands for Image Reduction um, and Analysis um, um, Facility, IRAF. And it was developed over, in fact, it's still being developed. It is open source, has been since the beginning. I think the first versions of IRAF came out in the mid 1980s. I started using it in 1988. Um, I was actually a member of the IRAF programming group for a couple of years, 1998 to 2000. So I'm probably a little bit biased. I know that there are lots of tools out there equally awesome, but I'm familiar with this relatively at least, and so I like it. So all this data um, was reduced and analyzed with IRAF, with all the IRAF tools, and so I thought that was very awesome. Um, so yeah, they got into it, and you know um, see, yeah, this is basically talking about how um, they identified these stars as um, yellow supergiants, and also identified that they were actually in the small Magellanic Cloud as as opposed to the Milky Way. But as I said, they found this one funny object, and it's like, what's going on? Well, maybe it's a foreground object. Well, uh, they uh, they satisfied themselves that it wasn't a foreground object inside of the Milky Way, that it actually was um, part of the small Magellanic Cloud. Uh, they convinced themselves uh, of that in a couple of different ways, looking at the metallicity, how much stuff that wasn't hydrogen and helium uh, was in this star. Um, let's see, how else did they do it? Uh, anyway, their what their conclusion was or is that this star is moving with such high velocity because uh, it was actually part of a binary system that in which one of the stars exploded in a supernova and flung this star out uh, at very high um, velocity. They actually think that in the next 10 million years, uh, it'll move. I mean, we'll see it move 1.6 degrees. So that's a huge amount. Given the fact, that this star is so far away, it is moving fast, moving very very fast. So, I was one of the pictures here. Uh, is just showing this one is just showing the small Magellanic Cloud. That's what this is. Um, I think the blue X's, yeah, are the other um, yellow supergiants inside of the small Magellanic Cloud. And there's a couple, that are outliers like that. Most of them, as you can see, are within sort of the galaxy itself. And this little red circle up here marks the location of this this star that supposedly has been flung out due to a supernova explosion. This was part of a binary star, and one star exploded and flung this guy out. And this red circle is a 1.6 degree, um, I guess, radius, 1.6 degree radius, uh, which just sort of shows how much this star um, could have moved, right? So it's possible. I think they decided that this star was about 30 million years old, um, and so uh, given its motion, it could have started anywhere within this circle, and as you can see, it does intersect the small Magellanic Cloud there, and so it could have um, originated, say, here, and a supernova goes off and has flung it out that way, that far. So that's pretty awesome. Pretty awesome. Let's see, what else do we have here? Oh, the other interesting thing, and this was the segue into this, is talking about how much data or how little data is actually required to you can spend months and months and months and years on very little amount of data. These are the observations that were made. So they observed this area 4 different times over a time span of 9 years. Well, eight and a half, 8.5-ish years or so. Um, Different telescopes, different instruments, and I'm going to take my handy dandy calculator, which is always within arm's reach, and I'm going to add up the number of seconds. You see the exposure time there in seconds? This is the actual amount of time used collecting the data that they uh, analyzed. It's a total of 5,100 seconds, which is 1 hour and 25 minutes. So 1 hour and 25 minutes worth of data went into all of this, and there's a lot there's a lot left because they have all of these measurements, right? And so each one of these stars, they're going to go back and look at in more detail as well. But so yeah, 1 hour and 25 minutes worth of actual collecting data time. That doesn't include you know preparing the observations, getting all the instrumentation ready, Um, it doesn't include, reducing the data, calibrating the data, making measurements, doing the analysis, writing the paper, um, submitting it to a journal. I think, did they say this is going into the astronomical journal? I think. Let's see, where does it say? Does it say? Doesn't say on here. I think it said on the uh, on the archive where it was submitted, accepted by AJ. So that is the astronomical journal, as opposed to AppJ, which is the astrophysical journal. So yeah, submitted it, uh, which means it goes, to referees, at least one or two. They write comments. It goes back and forth. Blah 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 blah. Finally gets accepted for publication and gets dumped into archive.org uh, just a few days ago, just a couple of days ago. I think this was put out on the 7th, the 6th, or the 7th. But yeah, just a little bit of data can take you a long, long, long way. These are spectra of some of the standard stars that they use to compare. Um, these are the H and K calcium lines. So we're actually seeing calcium in these stars. Here's the H delta line and the H gamma line, which of course is hydrogen. So you can see that this is actually the star, um, um, the flung out star. Doesn't have a lot of H delta, maybe not very much H gamma, and also not a lot of hydrogen, but a lot of calcium, which they're called, I mean, you can sort of characterize that as a metal, roughly speaking. I may not be saying that exactly right, but hey, I'm no expert. So this is, yeah, this is just how they were able, to classify it as an actual young supergiant. Young supergiant, is that the right term? Always get that wrong. YSG, young supergiant. Yeah, yeah. No, yellow supergiant. Yeah, yeah, yeah. Anyway, I thought that was a pretty cool paper. Pretty cool. So check that out for sure. This is, archive.org is sort of the bleeding edge of research. So maybe in the next week or two, you might hear about this star, that has been discovered, that was, flung out from some kind of a supernova event. Don't be surprised if you hear about it in the next week or two, because that's pretty cool. That's pretty cool. Um, the other thing that I wanted to mention, there's been a lot of news about the hexagon and the pentagon found at the poles of Jupiter, and I gotta tell you that was announced last January at the American Astronomical Society meeting. So I don't know. I mean, maybe people have short memories. Maybe people didn't pay any attention to that. For some reason, the AAS meeting wasn't talked about much on most of the podcasts that I watch, and that's kind of strange because um, the AAS talks. Uh, um, Most of the presenters, want to bring sort of that exciting new uh, breaking news about some kind of a discovery, and those images were shown at that time, and nobody mentioned them. And I mean, I saw them, and it's like, holy shit, what the hell is going on there? And but for 3 months, not a word until this past week. I think the papers were finally published, and you know, news organizations, are doing exactly the same thing I'm doing. They're going, to archive.org. They're going to, the journals, to get the latest news, and so my guess is that those papers were finally published, and so everybody's all um, um, they're all excited about them. But as far as I'm concerned, that's sort of old news. It's extremely interesting, extremely interesting. Um, I'm hoping that astronomers look at that and say, dude, we need to think outside the box here. We cannot limit ourselves to thinking like we have been thinking. And it's just hydrodynamics and gravity and heat. There's more. I mean, the fact that these things exist, um, and it surprises us this much, means that there's shit going on that we don't have a clue. We don't have a clue. So we need to start thinking outside the box, coming up with some explanations that are wild. Wild, we need explanations that match what we're seeing. I mean, this is crazy stuff. So let's come up with some ideas that you know match these extraordinary observations. Let's come up with some extraordinary theories to explain why. And to have an extraordinary theory, um, you have to think outside the box. All right, I noticed that it is past the 1 hour mark, and I deeply, deeply, deeply respect your time. Don't want to take any more of it up. You have a lot of choices when it comes to um, what you're watching and what you're spending your time doing. And so I greatly appreciate you watching this either now, live, or later in the future. Spread the word, subscribe, thumbs up, thumbs down, whatever it is. Make some comments down below. Share this. Share this. If you know people who also have a passion for astronomy, whether you're new, whether you're an amateur, whether you're an advanced amateur, or whether you're a pro. I invite you into this circle of friends for a fun, casual conversation, just talking astronomy for an hour. Uh, what can be better than that? I don't know. Not much. Not much. Maybe a couple of things, but not much. So, all right, I'm going to get out of here for now. Got to get back up to the ship. Uh, Productive day, and yeah, I think um, the tedious work of looking at more of my data is what's in store for me for a little while. I'm glad that it's cloudy because then I don't have to worry about going out when I have a lot of data to look at already. All right, I'm going to get out of here for now. Thanks for stopping in. Peace, cheers, and all of that. And I will see you on the spin less than 23 hours from now. Tomorrow night, um, um, Humanity Star is supposed to be passing over my location at about 7:15 p.m. local time. So uh, that's during this live stream. So I'm trying to decide how I'm going to do that. It looks like it might be cloudy, so it may be a non-issue. a non-problem, that is. But if it's clear, it's supposed to be magnitude 4.2, so I should be able to see it. Might even be able to photograph it with my smartphone. I can do a long exposure and get a streak. And I think I should be able to see a 4.2 magnitude object moving in the sky here. So we'll see how that goes. But yeah, so I don't know how I'm going to deal with that yet. I'm going to wait to see if it's clear or not. If it looks like it's going to be clear, then I might live stream from my smartphone. Um, don't know, because I'm also going to have to use my smartphone to photograph the event. So don't know how that's going to work out. Maybe I'll postpone it to 2:30 UTC. Maybe have a shorter live stream. Don't know. This live stream is evolving. It can change. Uh, this is sort of a one-off thing. All right, I'm going to get out of here for now. Peace out. And yeah, I will see you on the spin one way or another. All right, cheers.